Hi, my name is David. Today I'll show you a way to check for isomorphism using SageMath. To do this, we need two things. Number one, a download of SageMath, and number two, an understanding of adjacency matrices. SageMath is a free program based on the Python language that you can download on any computer operating system. To download SageMath, go to www.sagemath.org and follow the steps. Our examples will be done in Jupyter Notebooks using SageMath. Adjacency matrices should be a review topic for you, but as a refresher, an adjacency matrix is a square matrix which is used to represent a finite graph. We use a binary system to depict if two vertices are adjacent, where a 1 means the vertices are adjacent and a 0 means they are not adjacent. In this example graph, no vertex is adjacent to itself, but every vertex is adjacent to all their vertices. Therefore, the adjacency matrix depicted below the graph shows all 1s except along the main diagonal. Now that we have reviewed adjacency matrices and downloaded SageMath, you can build the matrix in two ways. The first way is how I have depicted in this new example, graph G. In my first line, I've saved the binary representation for each vertex as a separate vector. I then combine all of my vectors into a single matrix using the matrix function. The third output is not required, but it gives me an opportunity to check my work. You must now turn the adjacency matrix into a graph using the graph function. I have named the graph for later use. Graph H is done the same way, but I'll give you a moment to look over it before moving on to the next slide. The final command is to use the .is_isomorphic command. The output is true, so our two graphs are isomorphic for this example. Now with this simple example, we can clearly see that the two graphs are isomorphic even without SageMath, as you can see from the picture below the output. They are both simply a cycle. However, with a more complex example, can you see the benefit of using SageMath? Let's try another example. In this next example, I'll show you the second way to build the adjacency matrix using a new G and an H graph that are slightly more complex than the previous example. In the second example, the matrix is created without saving vector names. With this method, you can see how easy it is to get lost in the parentheses, square brackets, zeros, ones, and commas. To check myself, I printed the matrix to the screen. In this example, we see that G and H are not isomorphic. Let's look at the graphs again on the next slide. To show the two graphs, I've plotted them here above my original drawing. This is not a required action, and it does not facilitate us finding isomorphism with SageMath, but it does allow for a visual inspection of the graphs. Using this depiction, we see in graph H there are two triangles, 0, 1, 5, and 2, 4, 3. Or, using the original drawing, the triangles are M, N, R, and Q, O, P. However, in graph G, there are no triangles at all, so clearly these are not isomorphic. Again, imagine if these graphs had 100 vertices. A visual depiction for comparisons would be unrealistic. So can you see the benefit of using SageMath? Now that I've explained how great SageMath can be, I must give a warning. SageMath uses the Westfeller-Lehman isomorphism test. This algorithm produces a conical form, which is just a mathematical equation, for each graph. If the conical forms of the two graphs are not equivalent, then the graphs are definitely not isomorphic. However, it is possible for two non-isomorphic graphs to share a conical form. So this test alone cannot provide conclusive evidence that two graphs are isomorphic. In fact, the complexity of the graph isomorphism problem is also unknown. So is SageMath worth using? While a step-by-step explanation of the WL isomorphism test is beyond the scope of this lesson, it is relevant to know that it is based on iterative graph recoloring. So perhaps SageMath can help you as you create subgraphs and test portions of each graph as you work towards testing for isomorphism. For further reading, the original paper on WL isomorphism testing is titled The Reduction of a Graph to a Conical Form and an Algebra During this Reduction. It was originally published in Russia in 1968 and was believed to be a polynomial time solution for the graph isomorphism problem. However, a counterexample was found a year later that showed WL doesn't work for all graphs. Lastly, there's a very interesting story behind the disappearance of one of the founders of this algorithm. I hope you've enjoyed this so far. I hope to see you next time.